Hello, this is John Scherer,
I'm Lucas Bieblo.
And I'm Sierra Williams.
and this is our video for our final project for remote sensing fall 2022. In this video, we are going to first show some of the ideas we worked on at first, and then we will finish off with our final switchgrass project we did together. In the beginning, we toyed around with some code on Google Earth Engine. As you can see here are two examples. On the left, we have the maximum amount of dry days in a given year. And on the right, we have some playing around with NDVI in Scotland. Towards the middle of the semester, we may have gotten a little bit ahead of ourselves by going to the climbing wall and running a LiDAR scan on it. Our intention was to see if we could get a program to recognize the holds on the climbing walls. This proved to be a little bit over the top of our heads, so we continued to brainstorm from there.
So next we thought about building a predictive model for identifying high-risk areas for wildfires. This would be based off of a DEM, Landsat 9 imagery, the NLCD data, weather such as drought data, and burn area imagery. So to do this, we looked at taking a DEM, Landsat 9 imagery, and then burn data from the Northern California Central Valley, and then running these classifiers using random forest. Then to build the fire prediction model, we were going to use the trained random forest models and then insert the DEM, Landsat imagery, NLCD data, and then drought data. However, training more than one classifier using random forests and combining them proved to be rather difficult. And so we decided to once again reconsider what we might want to do for this project.
At this time, Professor Liu and Parth brought us in on a switchgrass project whereby they were trying to run object detection on this photo here. The goal for us was to help them draw sample polygons and to then have a model run off those sample polygons to see if the model could detect the bushes throughout the entire photo. After we drew our sample polygons, we wanted to see if we could take some of the work we had done during class and apply those polygons to some Google Earth Engine code. And for this attempt, we used the sample regions and the smile cart. And the first thing we had to do, of course, was to export our shape file from the samples that we made on the switchgrass. And then we had to import that shape file into our code, which you can see here as the sample variable. Our first attempt here produced an error because the properties only had one value across all polygons, and the classifier requires multiple values within that property. So our workaround was to create essentially a photo negative of the sample polygons, which would represent the ground, and that would be our second value within that property. Here is our placeholder polygon. As you can see, we just simply created a rectangle and then erased it with the polygons of the switchgrass. We would then merge this with the polygons into one shapefile. After merging into one shapefile, we then defined one of the fields, which we chose as shape length, to have a value of 1 for the box which was erased, and then for all other sample polygons a value of 2. And then we exported from ARC. This shows that merged shapefile in Google Earth Engine. However, for some reasons we couldn't quite figure out, it would only produce a gray bounding box, the same bounding box that we showed in the first slide of this Google Earth Engine attempt.
So this is the ortho photo that we were provided, and we ultimately collected and shaped out about close to 2,000 switchgrasses in the property. What we did was we carefully outlined the outer edges of the switchgrasses in order to capture the full extent of those grasses. So ultimately, we were able to run 3 successful deep learning modules through ArcGIS Pro's new deep learning modules. We were able to run 2 successful models with single shot detector and 1 with the faster RCNN. All 3 used a architecture backbone of ResNet 34, which uses 34 convolutional layers over a million image samples. In all 3, the learning rate was defined by previous iterations. So these were dynamic learning rates throughout the entire process. And ultimately, all 3 models achieved about an average precision score of around 60%. As you can see in the left single shot detector model, this was the first one we ran. We were able to process about 1,000 batches. In the faster RCNN, we were able to process almost 1,500 batches. And in the third test with the last single shot detector, we were able to process 800 batches. Ultimately, the faster RCNN model processed the most data with the best accuracy in the shortest amount of time.
So these 6 image patches were samples that were identified by the 3 training models. So the first single shot detector was able to identify switchgrass as an object and then not identify other objects that were in the image. It also did not identify the lawn that was outside of the area boundary.
Is that it? Is that all we need for this slide?
The faster RCNN processed the most data, but the second single shot detector had the most accuracy and identified the most switchgrass objects.
This is what the orthophoto looked like overall from the second SSD deep learning model. As you can see, it was able to identify quite a bit of the switchgrasses, though it does have quite a bit of gaps within the image. It was also tracking switchgrasses outside of the study area for a little bit. It was also picking up the vehicle and researcher that was standing outside. Overall, the deep learning model had a fairly good accuracy, and it was able to capture a lot of the switchgrass and leave out areas that were not switchgrass quite well. There is room for improvement on this model, but the overall result for this project is fairly well. Came out very well.